start, I want to thank you and to having me in this contributed talk. Our research is called Dynamic Origin of Conical Helix Magnetization Textures Stabilized by the Dzyaloshinskii-Moriya Interaction. We have published a recent paper, so if you have any doubts after the presentation, you can go deep in there. So our motivation is that magnonic is a branch of condensed matter physics that combines the study of waves and magnetism, trying to solve the loss of energy by heat produced by electrons passing through the matter and replacing them with spin waves. Nowadays, magnonic is studying spin waves propagating through saturated states and also through spin structures. So first, what is the nucleation field of a spin structure? If we have a high external magnetic field, the system will be in a saturated state. Is here the upper state where all the spins are pointing towards the magnetic field direction. But if we decrease the field under the critical field, the system will nucleate to a spin structure depending on the interactions that are in the system. So for example, here we have a magnetic vortex in a nanodisk, and principally we have two interactions competing here. In the edge of the disk, we have the polar energy trying to close all the field lines, while in the core vortex, in the center, the exchange energy tries to maintain the spins parallel to each other. So in each case, in the center or in the edge of the system, we have a competition between interactions, and this will happen always with any other interaction we will add in the system. Now we want to focus our research in the Dzyaloshinskii-Moriya interaction. This interaction appears when we have three main things: magnetism, spin orbit coupling, and any type of spatial symmetry breaking. The interesting thing of this interaction is that it produces chirality in the system. The chirality is an asymmetry property that describes a system that is distinguishable from its specular image. For example, the sphere is a non-chirality system, but our hand is a chirality system. And there are two types of symmetry breaking for the DMI. And one of them is the interfacial DMI that occurs in the contact surface between a ferromagnetic layer and a heavy metal. And the other type happens in non-centrosymmetric crystals, like the manganese, German manganese, and it's called bulk DMI. When we combine the dipolar interaction, the exchange, any anisotropy, and the Dzyaloshinskii-Moriya interaction, the system stabilizes chiral structures as skyrmions, a rise of skyrmions, helicoidal or conical states. We are going to focus in the helicoidal and conical states that are what we expect in thin ferromagnetic films. So here we have a phase diagram of a thin film of the external magnetic field as a function of the temperature. And if we are over the critical field, we have a polarized state. If we decrease the external field, the system will enter into a phase transition and change to a conical state. And if we continue decreasing the external field, we're going to reach the helical state. And we have to be careful because the temperature of the system, we have to study the system in temperatures under the Curie temperature in the case of ferromagnetism, because if we are above the critical temperature, the system will not behave as a ferromagnetic, instead will behave as a paramagnetic, and any any magnetic texture will stabilize in there. This area is the skirmion lattice. We are not going to study them in our research, but a lot of people wants to get this area bigger. About the dynamic properties, that the effects of the DMI and the dynamic properties is that produce non-reciprocity in the spin wave dispersion relation. Here, when we don't have DMI, the intensity of the DMI equals to 0, we have a dispersion relation, asymmetric dispersion relation. But when we put DMI in the system, we can see a non-reciprocity in the curve. And the interesting thing is that if we increase a bit more the DMI, there is a point that the frequency touches 0 at a critical wave vector, and this mode is called low frequency modes. The interesting part of this is that a few research have demonstrated that these low frequency modes are associated with the origin of different magnetic textures. For example, in this system that we have a magnetic field to the right and a easy axis uniaxial anisotropy to the top, we can see that when we decrease the magnetic field under the nucleation field, the system will create or stabilize a magnetic texture where the period of the texture will be related to the point, the critical point, where the frequency, the dispersion relation touches 0. So here we think that we're going to study the instability point of a polarized state from the spin wave theory and connect it with the nucleation of the conical helix structure in a ferromagnetic thin film with the presence of the DMI, that the DMI produces this type of magnetic textures. So at the right, we have the conical helix model proposed, where Q is the wave vector of the conical helix and is related to the period of the magnetic textures. And to the left, we have the system energy, we have the exchange energy, the Zeeman energy, the DMI, and the dipolar interaction. It's remarkable that the dipolar interaction is very difficult to calculate generally, and in most of the literature until recent papers, they approximate the dipolar interaction, and we put all the effort to calculate this energy. But when we do this, we realize from the spin wave theory that the model, the conical helix model, will not be circular, but will be elliptical and elongated to the plane because of the dipolar interaction. So to be consistent with this, in our model, in our research, we add the perpendicular anisotropy to have a circular conical helix that is in agreement with our model. So we can expect reliable results. And now, the idea of the research was if we have a connection between the nucleation field of the conical helix state that comes from the static properties of the system with the instability of the polarized state showed by the spin wave theory. So at the left, we have the nucleation fields calculated for different DMI intensities. And as Aharoni said, the system will transition to the state that have the bigger nucleation field. And we realized that when we calculate the relation dispersion from the same system, but in a polarized state, so the critical wave vectors matches with the conical helix wave vector from the magnetic texture. So, well, it matches the wave vector of both theories, and also matches the critical field in both theories. So we create a diagram, a phase diagram, to compare the static and dynamic properties of the system. And the black line, the black solid line, are the conical helix wave vector calculated with the static properties of with the conical helix model. The red diamonds are the wave vectors calculated from the spin wave theory, and the gray dashed line correspond to a bulk system compared to a thin film. In this case, we compared the polar energy when it's higher than the perpendicular anisotropy, so we will expect elongated orbits in the plane. And we can see here that the wave vector that is related with the period of the magnetic texture, or the period of the spin wave, we can see that the wave vector decrease, meaning a different state that circular conical helix. So in this area, we can expect elongated orbits, elliptical orbits. And when we have wave vectors equal to Q0, it means infinite wavelength. So this corresponds to a uniform state. So when we have a polarized state, when the DMI is under this critical DMI, we will have a reversion in the uniform state. And the other case is when the perpendicular anisotropy is higher than the dipolar energy. So we will expect elongated orbits out of the plane, and happen the same. The path of reversion could be an elliptic elongated orbits, but in this case, out of plane. And this difference between the spin wave theory and the conical helix model could correspond that our model describes a circular conical helix, and the spin wave theory is not limited to have a conical helix. The spin wave theory can describe an elliptic orbit from the conical helix.
Excuse me,
well,
Cristobal.
I know that.
You have only 1 more minute, so.
Yeah. Okay. Sorry. Yeah, I know that is a bit confused. You can see the paper for more deep understanding. It's a lot of information, but I try to summarize in the better way. Thank you for your attention.
Thank you very much, Cristobal. We have like 40 seconds for a question. If somebody wants to ask something, or else maybe we can find you later on Gather Town.